Professor Mondal for introduction, and I thank Academy for giving me the opportunity to present my research work in front of the distinguished scientists of the country. So, the title of my talk is Amorphous Carbon Thin Film as an Emerging Electronic Material. So, all of you know that carbon has many allotropes which are classified according to the molecular hybridization of carbon-carbon bond, and but the amorphous carbons is a disordered form of carbon with a broad range of carbon-carbon bond and bond length and bond angle. Though the crystalline forms of the carbon like graphene, carbon nanotubes, they have attracted more attention of the researchers, but amorphous carbon has attracted less attention. So, today I will show that how amorphous carbon can be used as a very good material in advanced electronics. Nowadays, foldable devices like foldable phone launched by Samsung and other companies, or some healthcare devices, they are becoming very popular. The key component of these devices is a foldable metal circuit. Nowadays, foldable metal circuits are conventionally prepared by encapsulating the metal circuit in between two thick polymer layers in top and bottom. Those polymer layers are called neutral plane. The role of this neutral plane is to compensate the stress developed while folding the metal circuit. But this method has many drawbacks. For example, as here the metal circuit is encapsulated between the thick polymer layers, so the heat developed cannot dissipate. So, the durability of the circuit reduces. And secondly, the thickness of these two polymer layers must be exactly equal, which needs very precise fabrication process. And thirdly, in case of health caring devices, there the circuit must be touched with the skin, so that it can receive the electrical signal from our body, but where this concept of neutral plane will not work. So, I have developed a method where the metal circuits are covered with an anisotropically conducting amorphous carbon thin film, which can conduct the electricity in the vertical direction, but in the lateral direction it has limited electrical conductivity. It is conducting up to 1 micrometer distance, and beyond that it becomes insulating. Generally, in the circuit board, the distance between the two adjacent metal lines is greater than 2 micrometer, and while folding the cracks developed has the size generally less than 1 micrometer. So, when we cover the anisotropically conducting amorphous carbon film over the circuit, then it can exactly follow the complexity of the circuit, as well as it can connect the cracks developed while the folding. So, you can see that this is the image of the micro LEDs are illuminating with the help of our hybrid amorphous carbon coated metal circuit at the extreme folding and crumpling condition. We have a granted patent on this, and now I will discuss how we synthesize this amorphous carbon thin film. Generally, graphene and other 2D materials, they are synthesized either by exfoliation or by CVD, either by top down or bottom up approach, but there are some problems, like those all the exfoliation is not very much scalable. So, lack of scalability, and CVD needs some sophisticated instrumentation, and generally synthesis time is required very long, and they are very much substrate specific. So, we have developed a synthesis method which is very easy, where we spin coat a precursor polymer solution over the whole 6-inch SiO2 Si wafer and just microwave it in household microwave for 1 minute, and then we get the amorphous carbon film over the whole wafer, and we can transfer that film over any desired substrate. We can precisely control the thickness ranging from 1 nanometer to 32 or 50 nanometer, and from the XPS we found that the film is nitrogen doped. We have another patent on this synthesis method, and when I transferred the thin film of different thickness over a conducting surface like ITO, then we found that up to 20 nanometer thickness of the film, the electrical conductivity of the film was exactly equal with the ITO. And when the thickness of the film gradually increased beyond 20 nanometer, then it gradually became insulating. And another experiment we did, we transferred the film over a gold circuit over PET substrate which is insulating, and there we have the gold lines situated at different distance ranging from 500 nanometer to 6 micrometer, and we measured the current at these points, and we found that when the distance between the gold lines is less than 1 micrometer, then the current level was very high and it is highly conducting, and when the distance is more than 2 micrometer, then the film becomes insulating. We also performed one conducting AFM study. There we transferred the amorphous carbon film over a gold pattern over the SiO2 wafer, and we measured the conducting AFM at the interface of gold and SiO2, and we compared the height map with the current map, where we found that the current was extended up to around 1.5 micrometer from the edge of the gold. This experiment also proves the anisotropic conducting behavior of the amorphous carbon film. This image shows that though cracks were formed in the gold circuit coated with amorphous carbon film, still the micro LED is illuminating with this, as the cracks are connected by the amorphous carbon film. From the AFM study, we found that the depth of the crack was 1 micrometer without any carbon coating, but with carbon coating the depth decreases to 200 nanometer. And this red line shows the stable electrical operation of the amorphous carbon coated gold metal circuit upon repeated outward, and this is for inward folding, but without any carbon coating the current level drastically fluctuates, you can see. And this amorphous carbon film has also outstanding protective capability. The silver nanowires are very useful material in the flexible electronics, but they are very much unstable. They get oxidized upon high temperature treatment or just exposure in the ambient condition for long time. But when we cover them with amorphous carbon thin film, they becomes very stable and their morphology and their electrical conductivity remains same. We have also used our amorphous carbon thin film in the enhancement of a thin film oxide based transistor performance. This is the scheme of the thin film transistor. Here we incorporated the amorphous carbon thin film layer in between the SNO2 semiconductor layer and the lithium aluminum oxide dielectric layer, and we found tremendous improvement in the transistor performance due to the reduction of the interfacial trap states by the ultra smooth amorphous carbon incorporation. We found that the trap states reduced by 2 orders, the saturation mobility improved by 7 times, and on off ratio improved by 3 times, 3 order. And you can see that with AFM we found that for the bare dielectric layer the roughness was around 0.9 nanometer, but in case of amorphous carbon coated dielectric layer the roughness reduced to 0.2 nanometer. So you can see that how smooth it became. And from the XPS also we found that this amorphous carbon film having nitrogen doping helps in the better growth of SNO2 layer. We can see the significant shift in the N1s region of nitrogen dopant of amorphous carbon film and the tin of SNO2 layer. Now I will discuss how amorphous carbon film can be used in deformable optoelectronic devices. Generally the conventional conductive transparent materials used in these deformable optoelectronic devices are metal oxides like ITO, FTO, or conductive polymers, graphene, carbon nanotubes, or metal nanowires like silver nanowires, or metal films, but they have many drawbacks, like some of them are very rigid. These has poor electrical conductivity, graphene and carbon nanotube. Metal nanowires, as I discussed, that they are poor environmentally stability, and metal film has poor transparency. So we have developed a ultra thin metal film which is highly conducting as well as very much transparent. So we found one interesting phenomena, that when we deposited silver, 10 nanometer of silver over bare SiO2 Si wafer, then we found that silver islands were formed which were disconnected from each other. So the surface was overall non-conducting. But when we deposited the same 10 nanometer of silver over amorphous carbon, then the islands get connected and it becomes conducting. The seed resistance became 20 ohm per square. And when to improve the conductivity more, what we did, we first deposited 1 nanometer of silver seed over the amorphous carbon, and then we deposited 9 nanometer of gold over that. Then the seed resistance further improved to 8 ohm per square. And from the XPA study, we found that the nitrogen doping of the amorphous carbon film helps in connection of these silver lines. That is why the surface is becoming more conducting. So this shows that how we prepared a transparent, foldable and stretchable ultra thin gold film electrodes over polymer substrate. First we made the 1 nanometer of silver seed and then 9 nanometer of gold pattern over the amorphous carbon in full wafer. Then we coated with some polymer like PVDF or PMMA, and then we dipped it into the water, and by peeling off we get the gold pattern over the polymer layer. And so we got the gold pattern over the polymer layer which is chemically connected with the amorphous carbon thin film. So to make it more deformable, we transferred another layer of amorphous carbon thin film over it, and we got highly deformable gold ultra thin film which is hybrid with the amorphous carbon. And then we used that in fabrication of foldable perovskite light emitting diode. This is the scheme where we used our hybrid ultra thin gold film with amorphous carbon as a transparent electrode, and then P dot PSS as the whole injection layer, and then the perovskite PEO polymer composite as the emissive layer, and again as the cathode. And you can see that under extreme folding our PLED is illuminating very well. And we have also fabricated one biaxially stretchable alternating current electroluminescence device with this is the scheme. This is our transparent conducting electrode, and here the emissive layer is ZNS copper PDMS composite. You can see even in twisted condition, in uniaxial stretching or biaxially stretching, our device is working very well. So in summary, I have demonstrated that we can synthesize amorphous carbon thin film, a very facile method, and in large area in 6-inch wafer scale. We can precisely control the thickness of the film, and we have utilized the anisotropic conductivity behavior of the amorphous carbon thin film to fabricate a foldable metal circuit. And this amorphous carbon thin film has also outstanding property as a protective layer to enhance the environmental stability of the easily oxidizable metal surface, and ultra smoothness of this amorphous carbon thin film was utilized to reduce the trap state, interfacial trap states between the semiconductor and dielectric layer of a transistor. And the nitrogen dopants of amorphous carbon film was utilized to fabricate a deformable ultra thin metal amorphous carbon hybrid thin film, which was used as a transparent conducting electrode in different display devices. And finally I want to say that though the main focus of the scientist community is over the crystalline materials graphene, carbon nanotube. There are still a lot of room in the amorphous carbon film that deserves more investigation. And these are some other research topics on which we are working: synthesis of epitaxial thin films, and synthesis of metal chalcogenides and their optoelectronic applications, surface modification of metal oxide nanoparticles, and biosensing application. I will be happy to collaborate with any of you. And now I like to thank my research grant agencies, my collaborators and research scholars, and thank you all very much for your kind attention. I will happy to have any questions.
Thank you,
Thank you, sir.
It's a very interesting amorphous form of carbon.
Thank you, sir.
Why is it conducting in a plane perpendicular to the film?
Yes, it has a, I will show this slide. Actually, this is very much dependent upon the synthesis procedure. If in our method, we are directly synthesizing the film over the SiO2 Si wafer. Here we spin coated the precursor solution, polymer solution over the wafer, and we microwaved it, and during microwave, abruptly within 10 seconds the temperature of this substrate becomes 350 degrees centigrade. So very localized graphitization is happening in the adjacent layer at the substrate. So this is becoming very much conducting, and gradually as it is going up, the distance from the substrate is becoming higher, then the extent of graphitization is decreasing. So there is some gap, we can see that there is some gap. So electrical conduction is being limited in the lateral direction, but in the vertical direction it is being facilitated, and also it is very much thickness dependent.
Graphitic film is also not so conducting in a direction perpendicular because of the van der Waals gap.
Yes, sir, it is very much thickness dependent also. We have shown that when it is very ultra thin, less than 20 nanometer, then it is vertically conducting, but gradually it is becoming like insulating.
So it's an amorphous structure with partial crystallinity.
Yes, there is very small grains of graphites. That's why conductivity is different. Thank you, sir.
So I'm curious to know that for such amorphous material,
Yes, sir.
is there some way you can get a little bit hint of the energy spectrum? Because of course, here there is no band structure. Because
Yes.
So that's a major problem of doing any type of theory on this.
Yes.
But, suppose if you do, let's say hypothetically, I don't know whether anyone done some artist type of things. What type of things you see? I'm curious to know that. It may be very naive question. I don't know about this.
Yes, sir. Actually, in amorphous carbon thin film means it has broad range of carbon-carbon length, and bond angles are also very broad, and it is very much dependent on the synthesis procedure. And still, people are working. I didn't do any theoretical calculation for this, but it needs more research.
There is no way to get experimentally any idea about its energy spectrum or anything like that, no? Because I don't know even how to define that, but just is there a particular way of, because of course you have talked about the various transport related measurement, more because in the normal solid state we try to understand the transport basically from the band structure. So that is why I am just trying to understand that whether in this case anything like that is possible or not.
Actually, sir, I don't have much idea about this.
Oh, that's fine.
Because it is anisotropically conducting, so in the vertical direction there should not be any band gap, but like
So there are crystalline material also which can have anisotropic conductivity. There also we try to understand
yes,
from the band structure, but
yes.
there is no such clue. That's why I am trying to get is there any
Yes, sir, that's why I told that more investigation is needed.
Thank you for this presentation. I only wanted to extend this question that was there previously. Are there any studies in the literature on let's say a scanning tunneling electron picture of the surface, so that one gets some idea of the two layers? It's about 10 nanometer at the smallest one said, so that one would like to get a greater idea as to the structure.
Yeah.
Is there anything in the literature?
Yes, there are some. Actually, before graphene came in the scientific community, there are many researches on the amorphous carbon and before 2004. So there are some STM study reports also, but we did not show any, we did not do for our material. So there are some reports.
Thank you.
Yes.
Yeah, I'm impressed by the simplicity of the procedure.
Yes, sir.
I'm just curious. I'm guessing that you have probably done the initial experiments in a common household microwave oven.
Yes, yes.
So I'm curious. I mean, how reproducible is this?
Yes, it is very much reproducible. Actually, we did at least means 5,000 times we did, and even class 10 student also can do this because it is very easy and very much reproducible.
No, but you control the time of this microwave radiation, or it must have required some amount of calibration.
Yes, and we also did in microwave reactor also to know the exact parameters. There also we have seen that we need 200 watt of microwave, and beyond that also amorphous carbon film will be formed, because in household there are some we can control the power, not very precisely, but even we found that from 200 watt it starts carbonization. Below that it will not form, so prolonged time may be required. So it is very easy, sir. And
just one more.
yes.
You mentioned about something about your where you have tried this biosensing applications. Could you just elaborate?
We biosensing, that is different. That is not with amorphous carbon thin film. That is with oxide materials, iron oxide. That is different thing from this. There I functionalized the surface of iron oxide nanocluster, that is magnetically very much responsive, and I functionalized the surface with some half fragmented antibody, and it was zinc doped. So zinc doping helped to attach the antibodies over the surface, and then we sensed the particular bacteria corresponding to this antibody, and we detected the bacteria from the milk using that antibody functionalized iron oxide nanocluster.
It's stable and
yes, very much reproducible.
Any more questions? One more. Okay, last question.
It's an interesting topic.
Thank you.
Ma'am, is there any other material or alternative material instead of amorphous carbon
For which application?
for electronic devices?
Yes, there are many. Actually, mostly people are working with graphene and 2D materials, like metal chalcogenides are also very good candidate, and carbon nanotube, as I mentioned, different crystalline allotropes of the carbon are taking the main focus. Yes, there are many.
So what made you to study about only the amorphous carbon?
Actually, this is very easy, as I discussed that we got actually, frankly speaking, we were trying to make some other material and we got this by God's grace, and then it became a blessing for us, and now we are investigating that it has many unknown properties which are doing excellent in different applications.
Okay.
Thank you.
With that, let's thanks again, Monalisa.
Thank you.